We use words like work, energy, and power all the time, every single day. But what do they actually mean? Well, in physics, these terms have some really precise and honestly kind of surprising definitions. So today, we're going to peel back the layers and see how understanding them can totally change the way you look at pretty much every single thing you do. Okay, so picture this. You're pushing against a solid brick wall. You're giving it everything you've got. Your muscles are burning, you're sweating, you're completely exhausted. You've clearly done a ton of work, right? Well, in the world of physics, the answer is a big, fat no. You have accomplished exactly zero work. How is that even possible? Let's figure it out. So, first things first, we've got to redefine work. I want you to forget about how much you sweat or how tired you feel. In physics, work isn't about effort, it's about accomplishment. It's a measure of what actually gets done. The physics definition of work is actually beautifully simple. Just two things have to happen. First, you have to apply a force, a push or a pull. And second, the object you're pushing or pulling has to actually move. It has to go some distance. If there's no movement, no matter how hard you push, there is no work. It's really that simple. Think of it like a super simple math problem. The work you do equals the force you use multiplied by the distance the object moves. So if that distance is zero, like with our stubborn wall, then the total work you've done is also zero. Doesn't matter how much force you put into it. And this is exactly where our everyday language gets us into a bit of trouble, right? I mean, studying for a test is mentally hard work, and just holding a super heavyweight study is exhausting. But in physics, neither of those counts. The real work is in the pushing, the lifting, the kicking. It's the actions that actually cause something to move. So let's just break it down into three simple rules. 1, you apply a force. 2, the object has to move. And 3, and this is a really key detail, the movement has to be in the same direction as that force. So when you're pushing on that wall, you totally nail rule number 1, but you completely strike out on rule number 2. The result? Zero work. And when we do successfully perform work, we measure it in joules. It's named after the physicist James Prescott Joule. Just to give you an idea, lifting a small apple about 1 meter off the ground takes roughly 1 joule of work. It gives us a real, tangible way to think about this stuff. Okay, so if work is the result, what's the requirement? What do you need in the tank to be able to do any work at all? Well, that brings us to our next big concept, energy. And this is the absolute key relationship. You can think of energy as the currency of the universe. If you want to perform 1 joule of work, you have to spend at least 1 joule of energy. It's the go juice for literally everything that happens. Now, energy basically comes in 2 main flavors. First, you've got kinetic energy. That's the energy of motion. And then there's potential energy, which is stored energy, kind of just waiting for its moment to be released. Kinetic energy is super easy to spot. I mean, it's everywhere you see something moving. A car speeding down the highway has a ton of it. A baseball flying through the air. A sprinter in a race. Even the wind turning a turbine. If it's moving, it has kinetic energy. Potential energy is a little more subtle. It's the energy of what if. A rock sitting at the top of a cliff has potential energy just because of its high position. A battery has chemical potential energy stored up in its bonds. It's all about capacity, just waiting to be turned into action. All right, so we have the accomplishment, which is work, and we have the ability to do it, which is energy, but there's a third piece to this whole puzzle, and it's all about timing, and that is power. Power brings the element of speed into the equation. It's not just if you do the work, it's how fast you do it. Power is the measure of how quickly you can spend your energy to get a job done. And the formula couldn't be simpler. Power equals work divided by time. Imagine 2 weightlifters lifting the exact same barbell. Now, they both do the exact same amount of work, but if one of them hoists it up in just 1 second, while the other takes 3 seconds, that first weightlifter is generating 3 times more power. We measure power in watts, and 1 watt is just 1 joule of work being done every single second. And yep, this is the very same watt you see on your light bulbs. It's telling you how quickly they're converting electrical energy into light and heat. And that's why it matters. A 100-watt appliance is way more powerful and uses energy way faster than a 50-watt one, and that has a direct impact on your electricity bill. So how do all these concepts, work, potential energy, kinetic energy, how do they all fit together? Well, they are all governed by one of the most fundamental, most important laws in all of science, This right here is the law of conservation of energy. It is an absolutely unbreakable rule. The total amount of energy in any closed system is always, always constant. You can't just make it from nothing, and you can't make it disappear. You can only change what form it's in. The classic falling apple is the perfect example. While it's just hanging there on the branch, it is packed with potential energy because of its height. But the moment it lets go and starts to fall, that potential energy begins transforming into the kinetic energy of motion. The form changes, but the total amount of energy stays exactly the same the whole way down. Which brings us right back to where we started, our wall. When you're pushing on it, you are burning your body's chemical energy. We know that for a fact. And we also know that energy can't be destroyed. So if no work is being done on the wall, where does all that energy you're spending actually go? The answer is heat. Your body converts that chemical energy into thermal energy through your muscle contractions. So you see, you didn't move the wall, but you did obey the laws of physics.